So I'm going to be talking about a paper that came out this week, which is why I was such a last minute addition to the panel. We looked specifically at what was the difference if we calculated embodied greenhouse gas emissions if we used a BIM that was prepared before construction or if we used on-site construction records. And the reason we did this is because if we want to make progress on embodied carbon, embodied greenhouse gas, it's important to understand where we're starting from. You can't change what you can't measure. So, just a bit about me. I'm a professor in civil engineering at the University of Toronto. And in my research group, we broadly ask questions about what's the relationship in between the infrastructure we build and our environmental outcomes, and where can we do better. We both look at questions of what we should be building and how we should be building. So this is the paper. The link here is free for 48 days still. So if anybody wants to check it out, if you copy that link, it'll take you to free open access to the paper. So specifically in this paper, we were asking how accurate and effective are current approaches for understanding embodied greenhouse gas impacts. And part of the reason we were looking at BIM is because there is increasing access and use of quick add-on tools for BIM to make embodied calculations one click or just to make them easier. And there's lots of reasons to why thinking these calculations should be really easy. Fundamentally, we need to know three things. One, how much construction material did we use on site? Two, how much energy did we use on site, either in terms of fuel burnt or electricity used? And three, what are the energy intensity or the greenhouse gas intensity of those fuels and materials? And you multiply them together and you get your embodied greenhouse gas emissions. So this is the case study project that we looked at. The bridge is now built. It was two twinned bridges going over two sections of river, as you can see in figure C, with a little bit of an island between. One of the bridges was expanded and twinned, and the other one was demolished. So we went over the course of the project from condition A to condition D. And then down at the bottom, you can see the dimensions of the final completed bridge. So we compared 4 case studies. One, we took the information in the BIM only, so the quantity takeoffs directly from the BIM, multiplied that by embodied factors from the materials, and came up with our base case BIM-based greenhouse gases, embodied greenhouse gas emissions. Then we adjusted this to closer to the on-site reality in steps. So first we said, we'll take the materials that were included in the BIM and we'll expand them to reflect what was measured in the QA/QC process. So that was step 2. Then for case 3, we said, okay, but there's a bunch of things not included in the BIM, specifically construction energy, also some materials, specifically rebar, that weren't included in the BIM. And we'll see how those change the embodied carbon assessment. And then finally, we checked the sensitivity to this to our choice in greenhouse gas impact factors. Part of the reason we did that is that there is a lot of research and discussion over the choice of what materials to use. Should we use a different concrete? Should we add slightly more additives? And we wanted to see how our uncertainty in how much we use compared to our uncertainty in what type of material. So this is the base case assumption on the left, and you can see it's about 1.25 times 10 to the 6 kilograms of CO2. And then when we adjusted that just based on the materials alone without adding anything that was missing to the QA/QC process, we saw huge increases in the embodied GHG. And this was because there were big differences in the materials used on site versus what had been expected in the BIM. And so when we look at that temporally, we can see that for the first 350 days, what was built on site tracks pretty closely to the BIM expectation, and then it starts to diverge pretty quickly. And why did that happen? Well, it was because they built a wall on site that they had not drawn in the BIM, in part because they hadn't expected it. And this change led to really big increases in concrete. But even without that, there were already more concrete used on site than in the BIM and more concrete used than the original assessment. We see similar impacts in the steel. Part of the lag here you see between deliveries and expected use is because the steel was stockpiled on site before construction, which the BIM didn't account for. And then another thing which we don't have figures for is there was way more asphalt use on site than there was in the BIM, in part because the road was repaved far on either side of the bridge, as is quite common on projects. And it doesn't make much sense to draw that because, a couple centimeters or inches of asphalt extending on either side, it doesn't give you a lot of information, which is what BIMs are usually used for. So when we were talking about this with our partner who had given us this data, we asked, how often are these types of discrepancies in quantities noticed between project planning and reality? And they said that the quantities are always accurate unless something changes on site. We said, okay, great. How often do things change on site? And they said always. They always change on site. This happens on every project. Usually that gets a laugh, but I can't hear any of you. So I'm just going to assume some of you are laughing. So the next thing we checked was if we add outside processes that aren't commonly modeled in BIM, like rebar and fuel, how does that change the embodied carbon assessment? And you can see again, we've gone from 1.25, we're now at about 4. So we've had a 212% increase in the embodied carbon assessment. And you can imagine that for all kinds of things we would use embodied carbon for, like regulatory filings or choosing between options, that type of change is pretty massive and can obscure choices that we would have otherwise have made. And then we checked the uncertainty, which I've just sketched on here. And the red bar shows the degree of change based on concrete mix. So concrete mix is important and we can do a lot with it. But on this case, the uncertainty from the concrete mixes or material choices was much, much smaller than our uncertainty from materials. So what's the so what? One was that the change was massive, well outside the margins of what we say are acceptable inaccuracies or uncertainties in this types of assessment. And part of it is because we don't make BIMs for greenhouse gas assessment. We make them for other reasons. Mostly at the moment, the two most popular driving factors are either visualization or conflict detection. And you don't draw a BIM for those reasons in a way that sets them up well for greenhouse gas assessment. So if we want to use BIM for embodied GHG, we have to draw them differently. We've got to put in a lot more detail, and we've got to take into account when we're doing the direct BIM greenhouse gas assessments that there's going to be a fair amount of inaccuracy in the BIM if we haven't drawn it specifically for greenhouse gas. In this case, it was a bridge, and a wall was the unexpected piece of construction or what wasn't drawn. But there's on almost every project, there's some significant part that isn't included in the BIM because it's rather direct or it's not part of the central question. Another thing to take away for it is that there is lots and lots of data produced on every construction project about how much materials we're using, which could be very helpful for future understanding of embodied greenhouse gas emissions. But at the moment, we're not usually collecting it. Okay, so that's a quick run through of that project. This is me, and I'm hopeful I will still be here at the end to take questions.